Now, one of the big places that we're going to stumble on irrational numbers is when we take a square root. Earlier, I claimed that the square root of a positive integer is either just another smaller positive integer or else an irrational number. And again, this is not something you should just take the math teacher's word for. This is something that's true for a reason, and we can prove it. I'm only going to prove it for the square root of 2. I'm only going to prove that the square root of 2 is irrational. We can do this in general, right? So for any number whose square root is not an integer, we can make this similar argument. But it gets a little bit tricky and the notation gets complicated. This is one of the many times in this class that I'm going to present you an argument. And your goal here is not to be able to duplicate this argument, right? I'm not going to put a question on a test where I say, prove that the square root of 2 is irrational. Your goal here is just to follow this argument and to understand why this is true. We're going to use a technique called proof by contradiction. We're going to assume that the square root of 2 is rational, and then we're going to find out that something impossible happens. So pretend the square root of 2 were rational. If it's rational, we can write it as a fraction p over q, and we can write it in lowest terms. So when we write a fraction in lowest terms, that means its numerator and denominator have no common factors. So what we're doing here is assuming that the square root of 2 is irrational, and we're going with the implications of that assumption. The first implication is we can write it as a fraction in lowest terms, because that's what it means to be rational. Okay, next we're going to think about, okay, what does it mean to be the square root of 2? The square root of 2, that's just the number that when we square it, we get 2. So if we take our p over q and we square it, we end up with p squared over q squared. So that has to equal 2. But also, right, 2 is an integer. We can write it as 2 over 1. Multiplying the numerator and denominator both by q squared, we get that 2 must be equal to 2 times q squared over q squared. And now we notice that these two fractions have the same denominator. If they have the same denominator and they're equal, then they also have to have the same numerator. So that tells us that p squared is 2 times q squared. That means that 2 is a factor of p squared, right? P squared is equal to 2 times something. That's what it means for 2 to be a factor. And 2 is a prime number, right? So we can't break 2 down into any interesting factors. In particular, we can't split it between the two copies of p. So it has to be a factor of p. So if 2 is a factor of p, we can write p equals 2 times something. We're going to call this something r. So p is 2 times this new number we're putting in called r. We're just going to use r to represent the number that p is 2 times. So p squared, the p squared that we had back here, is 2 times r squared because p is 2 times r. So that's 2 squared times r squared, which means the number 2 again, that's p squared over q squared. P squared is 2 squared times r squared, which is 2 times 2r squared. But now we have these two fractions that are equal. Denominators are equal, so their numerators have to be equal. So in particular, 2 times 2r squared is the same as 2 times q squared. That means 2r squared is the same as q squared. Okay, but now we have the same thing happening that we did earlier. 2 must be a factor of q squared, and it must be a factor of q. Wait, earlier we said 2 is a prime factor of p, and now 2 is a factor of q. That means that 2 is a common factor of those two numbers p and q. But that can't happen, right? At the beginning, we picked p and q so that our square root of 2 fraction that we were pretending to have, we picked those so this was in lowest terms. We picked p and q to have no common factors. So we picked p and q to have no common factors. And then we went ahead and found a common factor that they have to have if p over q is equal to the square root of 2. Which means we can't find a p and q like that. We can't write the square root of 2 as a fraction in lowest terms. So that means the square root of 2 must be irrational. And so that's the logic. That's how we know for sure that the square root of 2 is irrational. It's not just that we haven't looked hard enough to find a fraction that's equal to the square root of 2. It's that it's totally impossible to have a fraction that's equal to the square root of 2.